Non-singular matrices, one of the most important types of matrices in all of linear algebra. In the last lecture, we discussed the Gauss-Jordan algorithm, which takes any matrix and puts it in reduced row echelon form. In that lecture, we introduced a list of colloquialisms we use to discuss matrices, one of which was this term non-singular. What non-singular means is that the matrix is square and that its rank equals the number of columns, which is the number of rows. So in this lecture, we're going to see what's so important about non-singular matrices. So let's start with a question. Let's say we're studying a system of equations. So here the system we're studying has 3 equations with 3 variables. And remember, we can always represent our system as a matrix equation. In this case, the matrix equation is AX equals B, where A is the coefficient matrix of the system, X is the is the vector of variables, and B it organizes all of the coefficients to the right of the equal sign. So the system we're studying is AX equals B, and the whole point of the Gauss-Jordan algorithm is to solve for X. Well, you've been solving for X for a long time, so I think it's reasonable to ask a question. Why not just take the equation AX equals B and divide by A to get X equals B divided by A? This is a very reasonable question because this is how we normally go about solving equations with like normal arithmetic. Of course, the answer is, well, we don't know how to divide by a matrix. That doesn't make any sense in our vernacular. So the notion of a matrix inverse answers this question. So the inverses, we have to think carefully about them in the world of matrix algebra. But here's how they work. Let's say that we're studying an m by n matrix. That matrix might have left inverses. A left inverse would be a matrix L that we multiply A by on the left in such a way that we produce the n by n identity matrix. So if you take A and multiply on the left by L and you get the identity matrix, you call L a left inverse. Your matrix A might also have right inverses. This means that you could take your matrix A and multiply on the right by some matrix R and produce the m by m identity matrix. In this case, you would call R a right inverse. And an important thing to note here is that if A has both a left inverse and a right inverse, you can do a calculation. You can say L is really the same thing as L times the identity matrix because multiplication by an identity matrix does not change the matrix. But I sub m, the m by m identity matrix, is the same thing as A times the right inverse, so we can put that in. And remember, with matrix multiplication, the order that we're writing the matrices in matters, but the way we group parentheses doesn't matter. So L times the product A times R is the same thing as the product LA times R. And since L is a left inverse, L times A is the n by n identity matrix. And the n by n identity matrix multiplied by R is equal to R. So this chain of equalities tells you that if you have a left inverse and you have a right inverse, those two things have to be equal to one another. So if that's the case, then A has exactly one two-sided inverse, and we use the notation A to the negative 1. Okay, so let's see an example here. Here we have an example where we have 2 equations. We have this matrix A, which is 3 by 3, and it's involved in both the first and second equations here. In this first equation on the left, I'm taking A, and I managed to find another matrix I can multiply A on the left by to produce the identity matrix. So I take A, multiply on the left by this matrix, I produce the identity matrix. In this equation on the right, I take the same A, I multiply by the same other matrix, but now I'm multiplying on the right, and when I do this product, I get the identity matrix. These 2 equations tell me that the matrix I'm studying, A, has an inverse, and it's given by this matrix we've been multiplying by. So that's A inverse. It exists because we are presenting it in this equation. And consequently, what we would say here is that A is an invertible matrix. So if you manage to take a matrix A and you can find a matrix you can multiply on both sides by to produce the identity, you know that matrix is the inverse of your matrix, and you call it A to the negative 1. Now, we need to issue a word of warning here. There are many matrices that are not invertible. Here's an example. Here we have the matrix A, which is the identity matrix, but I've zeroed out the last one on the diagonal. If you take this matrix and you multiply by any other 3 by 3 matrix, you're guaranteed to produce a matrix whose last row is all equal to zeros. So what this is telling me is that if I take this particular A and multiply by any matrix, I will never get a 1 in the 3, 3 position. So consequently, this product can never equal the 3 by 3 identity matrix. So this is an example of a matrix A where no matter what I multiply by, I will never get an inverse. So you would say here that this matrix A is not invertible. So what we want to do here is we want to build a theory that tells us exactly when a matrix does have an inverse, and also we would like to know how to find the inverse. Now, why bother doing all this? Well, this answers the question that we started the lecture with. If you're studying AX equals B, why not just divide by A? Well, we don't have matrix division, but what we can do is we can multiply by the inverse, should the inverse exist. So here we have an example where we start off with a matrix A, and someone hands us the inverse of A, and we also have a vector B here. Now, when someone says that this matrix is equal to A inverse, what they are telling you is that if you were to take the original A and multiply on either side by A inverse, you will produce the identity matrix. Now, if you want to, you could solve the system AX equals B using the Gauss-Jordan algorithm. Remember how to do this. We take the original coefficient matrix A, we augment with the vector in question B, we do the row reductions, and we end up with a result. What we're finding here when we row reduce is that we get a consistent system with one solution. But in this example, I'm given more information. I'm also given the inverse of A. And if I have the inverse, I don't need to mess with the original coefficient matrix. I can just directly give my solution. If I have the inverse, the solution to AX equals B is equal to X equals A inverse multiplied by B. So the solution I'm looking for, X, is really just A inverse multiplied by B. And that gives me X. In this case, I see it's 10 to 4. The upshot here is that because I'm given the inverse, I don't need to mess around with the Gauss-Jordan algorithm and do a bunch of cumbersome row operations to get the reduced row echelon form. All I do is I take the inverse, multiply by B, and I get my answer. So I like this in a certain way, think of A inverse as like the key that unlocks the solution to many problems involving A. So what we're presenting here is two different ways to solve the same system. One way is the good old-fashioned way we learned last week, which is to, or I guess our last lecture, which is to take our matrix, augment with the vector, and then row reduce to solve the system. That will always work. But if we happen to have an inverse and someone gives it to us, we automatically know that the solution to our system is A inverse multiplied by B. So either way, what we're finding here is that this system has one solution, X equals 10 to 4. We found that when we row reduced the system, and we also found that when we took B and multiplied by A inverse. So we're getting the same result. It's just I'm trying to argue here that if we have the inverse, a more efficient way to solve the system is just to multiply B by the inverse. So now I'd like to state some properties of inverses so that we can wrap our heads around them a little better. Let's say that A is a square n by n matrix. What this theorem says is that if you multiply A on either side by another matrix B, and the result is the identity matrix, you automatically know that multiplying on the other side gives you the identity matrix. This is a great theorem because it cuts our work in half if we want to check whether or not a matrix is the inverse of another matrix. According to the definition, if you wanted to argue that a matrix is the inverse of A, you would have to multiply A on both sides to verify that you get the identity matrix. What this theorem is saying is that if the matrix is square, you only need to multiply on the left or on the right and verify that you get the identity. Because once you multiply on the left, it is automatically true that multiplication on the right gives the identity, and vice versa, as long as our matrix is square. So here we have an example. Here we're taking a matrix A, and someone gave me this matrix B, and I multiplied A by B on the right here, and I produced the 3 by 3 identity matrix. Right away, what I know is that I don't need to multiply A on the left by B to check that I get the identity, because my theorem tells me that if A times B is the identity, so is B times A. Consequently, I immediately know that B is the inverse of A. So this is nice. I only have to check one equation to check that this candidate matrix is actually the inverse of A. The last part of this theorem says that the only type of matrix that has an inverse on both sides is a square matrix. So only matrices that are square can have inverses, although we saw a previous example where we had a square matrix that didn't have an inverse. So whenever we're talking about matrix inverses, the punchline here is that we have to be talking about square matrices, and the whole point of inverses is that they multiply on either side to produce the identity matrix. What are some other properties of inverses? Well, we can now view this raising to the -1 to get the inverse as an operation. As long as A is invertible, meaning that the inverse is out there, we can view taking the inverse as an operation. And one amazing thing about the inversion operation is that it's order reversing. Remember, what this means is that if you multiply two matrices together and then take the inverse, that's the same thing as individually multiplying the inverses together, but you have to swap the order. The next property is the involutive property. What this means is that if you take a matrix, take its inverse, and then take its inverse, so if you take inverses twice, you always get back the original matrix. So this is our second example of an order reversing involutive operator. The first example we saw was the transpose operator. Our second example is now inversion. We have scaling rules. So if you take a matrix and scale by a number C and then take an inverse, that's the same thing as multiplying the original inverse of A by 1 over the original scalar. There's also transposition rules, or a transposition rule. What this says is that the inverse of the transpose of a matrix is the same thing as transposing the original inverse.